Hello everyone, my name is Hrushit Chaudhary. I'm a EEE 236 student and today I'm going to present on an organic field effect transistor. It is also known as OFET. That will be the general outline of our presentation. First we will go through the introduction of OFET. It will be followed by design of OFET. Then we will go through the device preparation. After that we will have a short discussion on transfer and output characteristics. That will be followed by discussion on current transmit in OFET, and at the end we will discuss advantages and application of OFET. Okay, so as I told you, organic field effect transistor is also known as OFET, and it uses organic semiconductor in channel. That's why organic word is used in OFET. It can be prepared by various methods such as vacuum evaporation of small molecules, solution casting of polymers or small molecules, and mechanical transfer of peeled single crystalline organic layer onto a substrate. The main purpose to develop this type of device is to get low cost, large area electronic and biodegradable electronic. OFET has various geometry in fabrication, but it generally used thin film silicon transistor geometry. In this geometry, gate is at the bottom with the top drain and source electrodes. SiO2 is generally thermally grown as gate dielectric. Sometimes methyl methacrylate is also used as dielectric. As we discussed, OFD generally uses thin film silicon transistor geometry. After the development in conducting polymer, the semiconductor properties of small conjugated molecules have been recognized. OFET area is developed very much in the past 10 years. The performance of OFET has improved more than the amorphous silicon TFT, which has field effect mobility that has the value of 0.5 to 1 centimeter square per voltage second. In general for OFET, if we have vacuum deposited small molecules, then mobility value is 5 centimeter square per voltage second. And for solution process polymer, it is zero point 0.6 centimeter square per volt second. So use of OFET is increased in industry. One of main advantages is that all layers of an OFET can be deposited and patterned at room temperature by a combination of low-cost solution processing and direct write printing, which makes them ideally suited for realization of low-cost, large area electronic function on flexible substrate. In general, thermally oxidized silicon is used as a substrate for OFET and SiO2 used as a gate insulator. We can deposit active layer of FET using various techniques as follows. Number 1. Thermal evaporation. Number 2. Coating from organic solution. And number 3. Electrostatic lamination. First two techniques are easier to produce but that have poor transistor performance. For coating, various techniques are used such as deep coating, spin coating, inkjet printing and screen printing. But in electrostatic lamination technique is based on manual peeling of a thin layer of a single organic crystal. It results in a superior single crystalline active layer, but it is more tedious. The thickness of the gate oxide and the active layer is below 1 micrometer. Here 3D image of OFET is shown. In this image, all layers are shown with the different colors, so it will be more easier to understand. As we discussed before, oxidized silicon is traditional substrate for OFETs, where the silicon oxide serves as a gate insulator. FET is usually deposited onto this, and current flow will flow from source to drain. Here, flow of electron is shown in the figure. It is same as the normal FET. When the sufficient gate voltage is applied, then electron will start flowing from source to drain. In this slide, we will discuss the transfer characteristics of OFET. Transfer characteristics of OFET is shown in this figure. The charge in the channel is modulated by adjusting the gate voltage. So we can say that device behaves as a variable resistance. When the gate voltage is below the threshold value, then the device is in off condition. And as soon as it reaches the threshold value, it starts conducting. A FET is basically a capacitor, where one plate is contributed by the gate electrode and the other one by semiconductor field. When a voltage Vg is applied between source and gate, majority carrier accumulate at the insulator semiconductor interface, leading to the formation of a conduction channel between source and drain. In the next two slides, we will discuss the output characteristics region of the OFET. In this slide, linear region of the characteristics is discussed. In the figure area, shaded by the blue color, shown the linear region of OFET. For various Vg's value, we get the different curve. Current ID is given by the equation, which is W over L Ci mu into Vg minus Vt into Vd. That indicates that the current value of drain is depend on gate voltage, terminal voltage, and voltage applied at the drain. So, as shown in the figure, when the value is below the threshold voltage, there is no conduction, and as soon as the value greater than the threshold voltage, it starts conducting. In this slide, saturation region of OFET is discussed. Saturation region is shown in the blue shaded region. For given Vg, when Vg is equal to the drain voltage, the electrical potential between the drain and gate is 0. So this destroys the capacitor created between the dope channel and the gate, and it will create the pinch off near the drain. So the channel is interrupted close to the drain, and we will have a constant current near the drain. It is shown by the blue shaded region in this figure, and after the saturation region, we will almost have a constant current. The current at a drain in the saturation region is given by the equation, which is W over 2L Ci into mu into Vg minus Vt square. It indicates that it depends on the gate voltage and terminal voltage. In next some slides, we will discuss carrier transport in OFET. The carrier transport in OFET is specified for two-dimensional carrier propagation through the device. Various experimental techniques were used for this study, such as Heinz-Shockley experiment on the transit time of injected carriers, time of flight experiment for the determination of carrier mobility, pressure wave propagation experiment for probing electric field distribution in insulator, and organic monolayer experiment for probing orientation dipolar changes, optimal time resolved second harmonic generation, etc. Carrier propagate through polycrystalline OFDs in a diffusion-like manner. They move through the conduction band in the best single crystalline OFDs. The most important parameter of OFD carrier transport is carrier mobility. Its evolution over the year of OFD research is shown in the graph of polycrystalline and single crystalline OFDs, which is shown in the next slide. In this graph, the horizontal line indicates the comparison guide to the main OFD competitors, amorphous silicon and polycrystalline silicon. The graph reveals that the mobility in polycrystalline OFDs is comparable to that of amorphous silicon, whereas mobility in rubrene-based OFDs approaches that of best polysilicon devices. In this slide, we are going to discuss advantages of OFDs. OFDs are generally less complex and it has a low cost fabrication. We can manufacture it at lower temperature, and it has a printable organic transistor as well. Its mechanical flexibility is high. Compatibility with the plastic substance is high. It is foldable and lightweight. It has strong optical absorption and efficient emission as well. In this slide, we will discuss the various applications of OFET. It is used in a flexible low weight and large area displays such as organic LED and organic TFT. It is also used in optical recording. Nowadays, electronic circuit printed on paper also use this technology. Due to its ultra low cost, low performance applications, it is used in smart cards. It is also used in low heat dissipation circuits. So at the end, we can say that organic electronics is ready to meet the requirements for the product realization. It has compatibility with a huge variety of substrate, reliability readouts according to the product requirements, its yield enabling the profitable manufacturing, proof of concept for simple and cheap manufacturing methods, and that realization of supply voltage that goes down to 1 voltage. Because of all these advantages, in last 10 years, the use of organic electronics is high. That's all from the my presentation of EEE 236. If you have any question, you can comment down in the box and I will be happy to answer those questions. Thank you.